Hello, I'm Michael McCoyd, and I'm presenting our joint work on defending against adversarial patch attacks. Adversarial patches are a type of adversarial example that only modifies a small area of the image. They go unnoticed by being small. An example might be a road sign with a band sticker on it that would generally go unnoticed by us. A patch attack is also more practical in the physical world. It is easier to put a sticker on a sign or on something else in a scene than it is to broadly modify many areas of the scene. We focus on digital attacks. They give the attacker more power. They're also easier to work with. The attacker can add a small square patch anywhere on the image with any content. We assume the attacker knows everything we know. They have full knowledge of our model and defenses. The attacker is limited to adding a 5x5 patch to the image for the data sets we examine. A 5x5 patch provides a good success rate on undefended models and is used in related work. We defend against this attack by getting predictions from overlapping occluded views of the image. Having clusters that predict unanimously for different labels suggests an attack. We size the occlude area to be slightly larger than the attack model sticker size, guaranteeing that the attack is completely hidden for several predictions. For instance, in this toy example, the two bottom right occlusions completely hide the attack. Here is an overview of our defense with a larger grid. We have overlapping occludes across the image. For each, we make a prediction. We assume that having even 1 pixel of the patch visible allows the attacker to change the predicted label. There will be several occlusions that completely hide the attack, such as here in the lower right that are predicting dog. Those predictions will be what they would have been if the attack had not occurred. Clusters that predict differently suggest an attack, such as the cluster of predictions for dog in the lower right and the large clusters that predict for cat. Let's look again at this example prediction grid, but with the original benign image. The underlying model that we're defending sometimes makes errors, particularly when we occlude pixels. For benign images, we see scattered errors across the prediction grid, sometimes individually, sometimes in clusters, but usually small ones. Let's look at an original image and an attack image based on it. The occlusions and predictions for the original are on the top half of the screen. Those for the attack image are on the bottom. For this low resolution image, we've set the occlude area to be 2 pixels taller and 2 pixels wider than the attack model patch size. And we stride the occlude across the image by 1 pixel. This ensures a crucial aspect of the defense, that the prediction grid always has a cluster of predictions that is unaffected by a possible attack sticker. Here, you can see that the attacker has changed all the predictions except for the 9 in the lower right. These 9 are where the attack sticker is fully occluded. Those predictions remain the same as from the original image before the attack. For reasons of space on the slide, we show only a portion of the prediction grids. Predictions on the original image have random errors as we expect, but we assume the attacker has complete control of the prediction if even 1 pixel of the patch is visible. So in the bottom half, the attacker has changed everything that they can change to the label of car. This is our full unanimous voting defense. Once we have our defense once we have our prediction grid, we consider if there are clusters of predictions for just one label or more than one label. As our occlude area and stride guarantee a 3x3 grid of the original predictions, our clusters are 3x3 windows into the prediction grid. For each window, we see if it votes unanimously for a single prediction. If it does, we add that vote to a voting set. For illustration, we highlight each window's vote in a voting grid before collecting them into the voting set on the far right. If a window does not vote unanimously, it does not contribute to the voting set. If our vote set has size 1, we label the image with that vote and as benign. If the vote set has size 2 or more, we label the image an attack. Here, most of the windows vote for car, while 1 votes for dog. So our vote set has size 2, and we label this image an attack. The pattern we see in this vote grid is what we expect from an attack. A window voting for what is likely the original correct prediction, dog, and most of the rest of the windows voting for the attacker's target label, car. But all our defense knows is that the vote set has size 2, so it labels this as an attack. Before we move to a more advanced and better defense, it will help if we use a richer representation for the prediction and voting grids. For this, we abuse Hinton diagrams. On the right is our new prediction grid. This is the same type of occluded prediction grid we have already seen. Just now, we use colors to represent different labels. The size of the squares indicates the prediction confidence. Just ignore the small orange bars and some squares. So the prediction grid on the right has many predictions for the class label 1, which we're coding as black, and has a few predictions for the class label 7, which we're coding as yellow. This was an example on MNIST. This is for a benign image, which we would classify as 1 and as benign. Here's our new prediction grid and a matching voting grid and voting set. This is an image we will classify as an attack. Most of the windows on the prediction grid vote for 3, black. The middle highlighted window votes unanimously for 5, yellow. The top highlighted window does not vote unanimously, so we leave its area in the voting grid blank, shown with the gray background. As the voting grid now contains votes for more than one label, we consider this an attack. But this is actually also a benign image, so calling this an attack is a false positive. Let's see if we can refine our technique. The prediction grid contains not just the predicted class, but also the confidence. Mispredictions in benign images tend to be less confident than the correct predictions. The yellow squares here are generally smaller than the black squares. We'll use this observation. In each window, we will exclude the prediction with the lowest confidence. Then we will average the confidences for each class of the remaining predictions. The class with the highest average confidence will be the vote with that average confidence. In the highlighted window, we exclude the bottom right prediction. Of the remaining predictions, 7 has the highest average confidence, so the window will vote for 7 with confidence 0.98. This is what our new soft voting grid looks like. We add votes to the voting grid for all windows, but we only pay attention to them if their confidence is above a threshold. Excluding the lowest confidence votes prevents scattered errors from changing the voting set we create from the voting grid. The threshold allows us to trade off between false positives and false negatives. If the voting grid has votes above our confidence threshold for more than one label, we say the image is an attack. Here, our confidence threshold is 90%, but there are only votes for one label anyway. So this is not an attack. Here, we have votes for two different classes above the threshold for our voting grid. Many votes for black, 8. 4 votes for yellow, 3. So we consider this an attack. To highlight which votes count, we gray out votes below our threshold. This is what we would expect from a good, though not idealized, attacker. The adversarial patch is likely fully covered by each occlude prediction in the highlighted voting window. The adversary has changed most of the high confidence predictions to their target label, but there is a 3x3 window of predictions they cannot change. Those were confident enough to appear in the vote grid, so we consider this an attack. They could also not change a few of the predictions where the patch was just short of fully occluded. Several of those remain confident enough to be above the soft vote threshold and show up as votes for yellow, 3, above the threshold. This is the most predictions that an attacker could hope to change. Everywhere except where the patch is fully occluded, the model predicts 3. Yet there is always a 9-cell window whose predictions cannot be changed by the attacker. Here, the predictions for 8 are strong enough to appear in the voting grid, as they are above our confidence threshold. This is an image vulnerable to an undetected attack. At any place in the voting grid with no vote above our threshold, the attacker could place a sticker that would go undetected. The 9 occlusions that hide that sticker would produce the same predictions as here in the original image. Those predictions would still not produce a confident enough vote to add it to the voting grid. The adversary can change every other prediction to the target class, thus filling the voting grid with confident votes for just the target class. The attack thus changes the classification and goes undetected. These have been the details of our defense. Now let's look at how well it works. We evaluate on 3 data sets, each with 10 classes. CFAR 10 is 32 by 32 color images of an object in a scene. Fashion MNIST and MNIST are 28 by 28 grayscale images. Fashion MNIST of clothing, MNIST of handwritten digits. We measure what the theoretically most successful attacker could achieve within the attack model. For us, that includes changing any occluded classification if only 1 pixel of the patch is still visible. That might be very hard to achieve, but it is theoretically possible. Evaluating the defense against such an attack certifies that no attacker can do better. We report 2 metrics. Clean accuracy is whether each image we classify, whether we classify it correctly in the absence of attack, properly identifying the class and that the image is benign. Certified accuracy means that additionally, under attack, the attack either does not change the class or we detect the class. We evaluate certified accuracy based on whether each validation image has vulnerable non-voting areas in the voting grid or areas already voting for the attacker's target label. This is how we compare to other certified results for CIFAR-10. We outperform interval-bound propagation and patch guard on both clean accuracy and certified accuracy. By varying our voting grid confidence threshold, we can trade off clean accuracy for certified accuracy. If we pick a clean accuracy of 91%, our clean error rate is 9%, while interval-bound propagation's clean error rate is 52%. And our certified accuracy is significantly higher than theirs. Our clean accuracy is 3% above patch guard, and our certified accuracy is 4% above patch guard. In summary, we provide state-of-the-art results against 5x5 patch attacks on CIFAR-10, boosting certified accuracy to 62% from interval-bound propagation's 30% and patch guard's 58%, boosting clean accuracy to 91% from interval-bound propagation's 44% and patch guard's 85%. Thank you.